Ja, perfekt. So ist es gut. Also Entschuldigung die Verspätung, dann können wir, denke ich, jetzt loslegen. Sie geben einfach Bescheid, wenn wir durchklicken sollen.
Ja, ich bin bereit.
Okay, vielleicht ich werde kurz vorstellen, Hermann Lühr, das ist eine große Gelegenheit, dass hat akzeptiert, dieses Plenarvortrag zu halten. Hermann ist ein Produkt von Braunschweig, ein Pure-Produkt sozusagen. Alles studiert, promoviert, bis zum Professor in Braunschweig geworden. Er ist wirklich ein Stern in dieses magnetic Community, übersichtlich, die mit Satelliten zu tun. So er ist the principal investigator from the CHAMP magnetic field investigations. He was also the project director of CHAMP. He was the German head of the SWARM project. This is the weltweit jetzt aktuelles großes Satellitenprojekt für Magnetdaten. Und wirklich, ich muss sagen, ein riesiger Stern. Er hat die Werner von Braun Medaille von der German Aerospace Society gehabt. Er ist ein Fellow of the American Geophysical Union, NASA Cluster Science Team Group Achievement Award, Julius Bartels Medaille of the European Geosciences Union. So without further ado, bitte Hermann, danke.
Yeah, thank you, Stuart, for your kind introduction. And I think I will give my talk in English, and I hope that I will reach more audience when talking in English about the topic here. Many thanks also, Stuart, for your invitation. And we should right away go to the next slide, please. Yeah, the geomagnetic field is, to first order, similar to a dipole in the Earth center. This is how the field lines look like. And this main part of the geomagnetic field is generated in the liquid core. An important feature of the geomagnetic field is its ability to shield us from dangerous radiation from space. Yeah, next, please. Here I will lead you through a journey through temporal and spatial scales in my talk. I will talk a little bit about geomagnetic field modeling, then the role of the magnetic field for remote sensing, and also for sensing electric currents. Finally, I come with an outlook, and in the end, I will give you a comprehensive list of all the references I'm citing here. Yes, next, please. The important part is a geodynamo, and this is a thermal engine in the center. It's driven by the hot inner core, and this is driving convection motion in the iron, in the buff-lying fluid core. Due to the rotation of the Earth, the motion goes in spirals, and it moves from the equatorial region up to the polar region. And within these flux bundles, most of the magnetic field is generated. The process is very unpredictable, and sometimes it even can change the polarity of the whole magnetic field. And during these times of magnetic field changes, the field strength is very low. That means we will have only a weak shielding effect from the geomagnetic field. Next, please. As I said before, the polarity of the magnetic field has changed frequently in the past. Why do we know it? Because rocks and sediments are a wonderful archive for storing the magnetic field direction. And as soon as this material cools down below the Curie temperature, it preserves the ambient field. Presently, We are in the Bruns phase. You see it on the left side. And this is lasting for already 780,000 years. Before you see a lot of field direction changes over the past. But when you go back about 100 million years, then there was a period of very stable magnetic field. This is the Cretaceous normal chrome. It lasted for about 30 million years. And next, please. In between these total field reversals, we also observe so-called excursions. And these excursions are characterized by a number of features. For example, the direction of the field, or here we call it the virtual geomagnetic field pole, is moving by more than 45 degrees away from one of the poles. And furthermore, the field strength goes down to below 25 degrees. And this effect should be observable globally, but not only locally. Yes, next, please. Here we see an example. Yodo and Vallée made use of their SYN 800 model and reconstructed the magnetic field strength variation over the past 800,000 years. That is just covering the Bruns phase. And what you can see that during certain times we had quite a large dip of the field strength. These are the so-called excursions. And the most recent one, the so-called La Chambre, to the left in the figure, that is rather good investigated in the past. And when you look to the right figure, then you see in the bottom frame that the field strength around 40,000 years ago dipped down very deeply. Only 10% of the previous field strength was left. That means then we probably had a very poor shielding of the magnetic field against the ambient radiation. Yeah, next, please. In the more recent past, we have also other indicators for the magnetic field. For example, artifacts, pottery, or ice samples. And with the help of these archives, quite reliable estimates of the magnetic field variation have been obtained. You see down there several curves of the magnetic field variation over the last 10,000 years. And from the various studies listed there, you can see that they more or less all follow the same trend. The magnetic field strength was strongest around Anno Domini. At that time, it was about 40% higher than today. But after that, the field strength is continuously decreasing. And in the right panel, you see the magnetic field decrease, that is a dipole moment decrease, since the day of direct observations around the time of Gauss. And it follows a nice linear trend of about -1% per 20 years. Yeah, next, please. Why is it important to know the magnetic field? In the past, this was easy to answer. People were using the magnetic field for navigation. They used the compass, and this is in particular true for the ship. In those days, a lot of effort were spent to map the magnetic field over the Atlantic Ocean. Edmund Halley was the first to come up with a full map around 1700, but it soon became evident that the magnetic field direction is continuously changing. And when you, for example, look at the red line, that was the region of zero declination in those old days, but more recently, the line of zero declination has moved far to the west, and it's even west of South America now. Yeah, next, please. The situation has improved enormously with the innovations of Carl Friedrich Gauss. He, for example, invented the techniques of absolute calibration of magnetic variometers, and he also defined a common time base, the so-called Göttingen time. With these two technical innovations, it was possible to compare magnetic field observations at stations located very remotely from each other. And the second one is that he made use of the spherical harmonic functions for describing the magnetic field. His assumption was that the magnetic field can be treated as a scalar potential field. You see down there is the basic equation. We have on the left the term, the dependence of the radial components. Then in between, there is the dependence on the longitude, that is the lambda dependence. This is a kind of Fourier transform. And to the right, there is the dependence on the latitude. So the Fourier transform is weighted by the latitude function. And the magnetic field components can be derived by the negative gradient of the potential. Next, please. Yes. Gauss was the first to come up with a global map of the magnetic field. So it was no longer necessary to map the whole ocean. He could do it in one run. And in spite of his fairly low number of observatories, something like 30, and in particular, the very uneven distribution of observatories, mainly in Europe and only few overseas, he could come up with a very good map for the magnetic field. And this is just because it shows the power of the spherical harmonic analysis used for the magnetic field representation. This is also the reason why we still today use this approach for the main field modeling. And next, please. Yes, a further big improvement came with the satellite era. NASA's MAXSAT satellite was the first to make magnetic field measurements in the 1980s, but only for 6 months. And the satellite was only sampling the dawn and dusk meridian, so we didn't have a full local time coverage. About 20 years later, the Danes came with the Ørsted satellite. This satellite was making measurements from 1999 to 2004, vector measurements. After that time, the vector instrument failed, and only scalar measurements were available for the year after. The real breakthrough came with the CHAMP satellite. It was the German CHAMP satellite that was in orbit from 2000 to 2010. And in particular, it was flying at low altitude, which is important for high resolution. And furthermore, it covered all local times within 130 days. The success of the CHAMP mission inspired ESA to build 3 identical satellite, CHAMP-like satellites. And these are now in orbit since 2014. And we hope they will stay there for a long time. Next, please. Here again, you can see the satellites CHAMP and SWARM. You see they are very similar in shape and also instrumentation. Below you have as a black line the orbit of CHAMP. It starts off at 450 kilometers and then gradually decays. And the good thing is that the lowest part of the orbit, around 300 kilometers, is just coinciding with a very deep solar minimum. And that means we could make undisturbed measurements at lowest altitude. The CHAMP satellite, the SWARM satellites are shown in green and red, and they fly at 2 different altitudes, somewhat higher, and we hope they will be in orbit for at least 10 more years from now. The hard piece of the mission is the so-called optical bench. This is the encircled instrumentation package. Below you see a blow-up. You have the vector magnetometer as a red ball in the front of the tube. On the other end, you have 3 star cameras which give a precise orientation of the magnetic field measurements. Yes, next please. The advantage of magnetic field measurements is that you get a very good global coverage. What you can see here in the top panel is the coverage of the SWARM satellites of only 5 days. But that is, of course, already good enough for making a decent geomagnetic field model. In addition, we have about 100 intermagnet observatories. And these are unfortunately not very evenly distributed. You see a strong clustering over Europe, but also large gaps over the Pacific, Atlantic, or South, or the Indian Ocean. Nevertheless, the measurements of these ground observatories are very valuable for the interpretation because they provide continuous measurements of the temporal variations, which cannot be achieved by the satellites. The satellite is moving both in time and space, and it's not so easy to separate the things. Next, please. Here is just one product from the measurements. This is a rather recent magnetic field model from SWARM nowadays. And this, due to the combination of the satellite and ground-based measurements, the model is so precise that it has to be updated every 6 months. Otherwise, you lose the precision because the magnetic field is changing in an unpredictable way. In the right corner, you see the spectrum of the magnetic field measurements. In the red line on top, you have the dipole moment that is quite outstanding, but the higher degree terms, they drop off like a power law, and this power law decay is consistent with a wide source of signal at a depth of 3,000 kilometers. And 3,000 kilometers is just the depth of the core mantle boundary. That means, obviously, the signal is coming from the core mantle boundary that we are observing. If you go to higher degrees, higher than 15, and so then you see a flat spectrum that is caused by the crustal magnetization. And you also can see that the long wavelengths crustal terms are masked by the core field, and vice versa. The high degrees of the core field are masked by the crustal magnetization. So therefore, we have blanked out part of the information. Yeah, next, please. Here I repeat again the compilation from Gauss, and you should look to the similarity of the modern magnetic field distribution, and that derived from the few stations of Gauss. You have the two field strength maxima in the northern hemisphere. You have the one field strength maximum in the south. And you also see the lowest point in the South Atlantic from the Gauss compilation. Nowadays, this point is still there, but it has shifted further to the west. Actually, Gauss was the first to identify this so-called South Atlantic anomaly. From all the measurements before, it was not evident. Yeah, next, please. Yes, coming back to the variation of the magnetic field. I've shown you that the dipole strength is decaying by 1% per 20 years, but this decay is not evenly distributed over the Earth. Here on the left side, you see a comparison between MAXAT and CHEMP measurements that spans the time of 30 years. We see a slight increase of field strength over Europe and Asia, and also a little bit in the Indian Ocean. But over the most parts of the Earth, we have a decrease, and particularly strong in the South Atlantic and over the Americas. To the right, there is another comparison between the 10 years CHEMP and SWARM. And here you see a rather similar distribution, also a little bit more detailed because it has continuously good measurements. But what you can see is that the regions where the ambient magnetic field already now is weakest, you observe the fastest decay. Here we have a reduction of field strength of 3.5 degrees in 10 years. That is 10 times faster than the global dipole decay. That means the South Atlantic anomaly deeps very rapidly. Next, please. Yes, this strong reduction in field strength has quite an effect on the shielding. For example, you can see that in the region of the South Atlantic anomaly, it is in the left frame, the colored part. In the center of this South Atlantic anomaly at an altitude of 500 kilometers, where many of the satellites are flying, the radiation is enhanced by more than a factor of 100. And this will further increase with the further decrease in field strength there. The consequences are directly observable. In the right side, you see satellite anomalies of the TOPEX Poseidon satellite, and all the white dots are more or less concentrated within the area of low field strength. And you can almost see that the density of the dots is proportional to the darkness of the color. This continuous decrease will probably have consequences for the astronauts on the space station and also on the satellite operations. Probably satellites in future have to be built more robust to withstand this radiation. Next, please. A very important product of the CHEMP mission is the compilation of crustal magnetization. And this map contains a big lot of information, not easy to explain here, but what you can generally see is over the continents, the magnetization is stronger. and then over the oceans. But this is not generally the case. For example, when you look at Europe, then you see that the eastern part of Europe, where we have the old crustal shield, it's very magnetic, but the western part of Europe is much less magnetic. And that has to do with the age. The western part of Europe is a fairly young crustal, of young crustal age. Also visible are these lineaments in the Atlantic Ocean, for example. These are the so-called ocean stripes. And when you look close to the American coast, there is this orange part, and also in the African side, there's also a little bit orange part. That is the time of the Cretaceous normal chrome. So 30 million years with the same polarity. They gave a rather clear signature there. And otherwise, you can follow these ocean stripes. They are comparable with tree rings. From the distance of these ocean stripes, you can determine the expansion rate of the ocean bottom. For example, you can also see that Greenland was moving away from North America only up to the year or up to 100 million years ago, and then the Atlantic Ocean opened on the east side of Greenland, where it's still opening today. Next, please. Yes, here is now a detailed feature. What you can see is the islands of Indonesia. You have the island of Sumatra and Java. And on the shore side of these islands, you have the orange colored line. That means stronger magnetic field. This marks a cool region where the ocean slab is subducting. And if you go onto the islands, you have the blue color that is reduced. Magnetization, that means you have hot material below the islands, and it's no surprise that we have so many volcanoes there. You see more of these orange-blue stripes. All these are subduction zones. So the magnetization of the crust also tells us about plate tectonics if we look close into that. Yeah, next, please. So far, I have told you about magnetic fields from the main field, from the crust. From that, we have in the meantime so precise models that we can look for deviations of the observations from these models, and these signals provide interesting information about other processes. In that sense, the magnetic field can be used as a remote sensing signal. Next, please. One impressive example for that is the magnetic signal of ocean tides. When ocean current is driving salty water across magnetic field lines, then electric currents are generated, and these in return produce magnetic fields. Schempp was the first to identify these tidal signals. And on the right, in the top frame, you see the magnetic signature of the tides at the epoch of new moon. You see blue and orange patches. That means it's positive and negative field strength deviations. The frame below shows the tidal prediction from ocean models. And it's surprising to see how well these two agree with each other. And if you look further down, you have another example. This is 6.2 hours later. That means 90 degrees in lunar tide later. The picture has a little bit changed, but again, the comparison with the tidal model is very promising. The model is just a little bit smoother than the observations, but this is expected because models tend to smooth out things. Yeah, next, please. We also made some tests, and therefore we took only data from this rectangular at the North Atlantic region. And when we do a Fourier transform of that spectral analysis, we get a very clear narrow peak of the lunar M2 tide, which occurs at 12.5 hours, and no comparable signal somewhere else. We tried the same with a box to the right over Asia land mass, and that is the gray line, and the gray line that you see on the left has no peak at the lunar tide. So the signal that we have interpreted here is definitely caused by the tidal motion of the ocean. Next, please. Magnetic field signatures can also be used for determining ionospheric irregularities. Here you see at the black line the plasma or electron density variation along the satellite track, and below is the total magnetic field variation. Both these signals vary nicely in antiphase. And the reason for that is the diamagnetic effect of plasmas. If you have a depletion in the plasma density, then the plasma pressure is reduced, and this reduction is compensated by the increase of magnetic field pressure, so that we have a balance in total pressure over the time. Next, please. This effect has been intensively used by CHAMP for finding irregularities in electron density in the ionosphere. The bottom curve shows measurements of the electron density, Ne, and there are depletions from time to time. And whenever there's a depletion, the total magnetic field has a positive excursion. Just the magnetic field recordings show more structure. That's because the magnetic field is measured as at a rate of 50 Hertz. That could therefore resolve much better the electron density distribution within these dips. Next, please. Why is it important to look at the irregularities in the ionosphere? This is because the GPS signals are badly disturbed and scattered when they go through such a region of irregularities. Therefore, it would be interesting to know when and where these irregularities occur. Next, please. Next, please. Yes, thanks. Here you see the distribution of the irregularity occurrences derived from the magnetic field measurements, and they are shown with their seasonal variation from month to month versus the longitudinal distribution. Quite surprising is the high occurrence rate during December, January over Brazil. And if you go, for example, to June and May, there is nothing going on over Brazil. On the other hand, if you look at Africa, there are a lot of these disturbances in May, June. And so you can go in other places and other times. All that means the appearance of these disturbances are not randomly distributed, but they show a very distinct longitudinal pattern. Next, please. Yeah, an important thing of magnetic field measurements is, of course, also detecting electric currents. And you probably know this current probe approach. You have an electric conductor going through a ferromagnetic ring. And when you measure the magnetic flux through the ring, then you can determine the current strength. We made use of the swarm satellites. You see in the right corner, these two satellites flying are side by side. And these are the satellites swarm A and C. And in the left corner, you can see the measurement approach. We first took a measurement from swarm A at 0.1, and 5 seconds later, a second measurement at 0.2. Similar with satellite C, first at 0.4 and then 0.3. And with the help of these 4 measurements, we perform a ring integral. This is Ampere's integral law, and divide the integral value by the area A within the contour. And from that, we get the current density. In the case of swarm, 5-second difference means a distance of 38 kilometers. That is the path the satellite is traveling. And the east-west separation of the two satellites flying side by side is 1.4 degrees in longitude. This distance is, of course, changing with latitude. And at auroral regions, it is about 50 kilometers. So that means we can measure current densities of all the features which are larger than 50 kilometers in scale. When you're interested in the field-aligned currents, then you just have to project the vertical current component onto the ambient field direction. Next, please. In the ionosphere, we have a number of different current systems. At the high latitudes, they are particularly strong. There we have the field-aligned currents here in yellow. And in the ionosphere, we have the polar or auroral electrojets in green, flowing around the magnetic pole. At mid-latitudes, we have the SQ current vortex, one in the northern hemisphere, one in the southern hemisphere. And at the equator, there is this equatorial electrojet. And I will talk about all 3 of these current systems. Here to the right, you see an example of field-aligned current measurements with the CHAMP approach, swarm approach, and the orange, yellow marks upward currents, blue marks downward currents. When we come from the low latitudes, then we first approach the region 1 currents, then the blue is the region. No, sorry. When we come from the right side, 6 o'clock, then we approach first the region 2 current system, then the region 1 current system, and then the region 0 current system. And on the evening side, it goes the other way around, 0, 1, 2. I could spend a whole talk about this current system in the Northern Hemisphere, but I don't want to do this here. Therefore, I would say, let's go to the next slide. Yes, here we come to the SQ, solar quiet current system. When you look at a mid-latitude magnetogram on quiet days, you often find this daily variation that is in the east-west component the first positive, the negative variation. In the north component, it's a negative dip. And in the vertical component, it depends on the conductivity of the ground below. The SQ system forms two current vortices, one in the north and one in the south. And in the center point, maybe not so clear to see, it is a so-called focus. This is a current system that only flows on the day side. Therefore, you see nothing going on the night side. The current is more intensive in the summer hemisphere. If you look to the right, it is the 1st of July, as strong in the northern hemisphere and only weak in the southern hemisphere. The opposite is true for the 1st of January example. There you have the strong southern hemisphere vortex and a weak in the northern hemisphere. During the equinoxes, the intensities are more or less the same. These figures have been derived by combining ground-based and satellite data. And with that, you have the ionospheric currents sandwiched in between the two observations and can get very precise and detailed representations of these current systems. What you see here is for 6 o'clock UT, but I could also present for every hour, for every UT hour, such a plot and show you how this varies over the day. The next, please. It has been it has been assumed many years ago that there is a current flowing between the SQ vortices from the winter hemisphere to the summer hemisphere. And you know, the winter hemisphere vortex is very weak and in summer is very intense, at least around noontime. In the morning, an opposite direction current had been predicted, and in the evening also from south to north. In the middle, you see observations from our swarm satellites. And there you can clearly see that for the June example, there is a strong current from the southern hemisphere to the northern hemisphere around noon, as expected. And also a current flowing from the northern hemisphere to the southern hemisphere in the morning. In the evening, we have also observed also a current from the northern to the southern hemisphere. That is opposed to the direction of the prediction. The thing is totally different when we go to the winter season, when we expect a strong vortex in the southern hemisphere. We suddenly, for the December solstice months, no interhemispheric currents at all. No clear signature for that. And if any, then they are in the wrong direction. Furthermore, it was predicted that these interhemispheric currents are connecting the SQ foci. That is the middle point. These are located at about 35 degrees magnetic latitude, but just at that latitude, we find no interhemispheric currents at all. And even worse, north of it, we even find opposite current directions to the lower. So therefore, we get a quite different picture for the interhemispheric current than the predictions. We have a set of currents below the focus, a set of currents and opposite currents above the focus, and we have no clear interhemispheric current around December solstice. Well, that is an open question that has no good explanation today. Next, please. Now I come to the equatorial electrojet. That is a intense narrow current flowing right over the magnetic equator from east to west. No, sorry, from west to east. And it is also confined to the day side. In the top left frame, you see magnetic field measurements. And the large scale variation is the SQ current system. And on top of that, there is this narrow feature that comes from the equatorial electrojet. We were inverting these magnetic signatures in terms of magnetic current density. And there you can see that the current peaks right at the dip equator. And in some cases, you have also currents in the opposite direction in the sidebands. Next, please. It was long time under debate. What is the real longitudinal distribution of the equatorial electrojet intensity? But the number of ground-based observatories was not sufficient to answer this question completely. Only with the help of satellites, it was possible now to get an understanding of the longitudinal distribution. What you can see here in color is the peak current density of the electrojet, and it is shown in local time versus longitude frames. And what you clearly can see is that this distribution of electrojet intensity changes rapidly or drastically from season to season. The reason for this pattern, for these longitude patterns, are tidal winds in the upper atmosphere. These tidal winds drive the current, and they change drastically from season to season. Therefore, the electrojet is a very sensitive indicator for the dynamics in the upper atmosphere. We will come later to other examples. Next, please. For testing that, we were looking at the distribution of thunderstorm clouds at low latitudes. In the lower part, you see the cloud density derived from CHAMP radio occultation measurements. And right below each of the electrojet intensity maxima, you find strong thunderstorm clouds. These thunderstorm clouds generate non-migrating tidal waves of the type DE3. D means diurnal variation and E means eastward propagation. And if you, the next slide, please. If we plot the phase fronts of these DE3 tides onto the electrojet signals, we see a wonderful match of the activity distribution, and you see the eastward propagation over the day, as it says. So this longitude structure is definitely determined by the tidal activity. Next, please. There is another interesting phenomena in the upper atmosphere, that is the so-called stratospheric sudden warming. During winter time, strong wind vortex is forming over the North Pole. And this strong wind vortex is enclosing very cold air, and this cold air cannot escape. But in the 1950s, a group of the Freie Universität Berlin discovered that in some years, warm air from the Pacific Ocean is moving poleward and then splitting this cooled vortex, shifting the cooled air to the North America and to Siberia. These years then are called years of stratospheric sudden warming. The interesting part of that is that this effect, which is just a climatological effect, is also strongly influencing the equatorial electrojet. To the right in the top, you see recordings of the electrojet from the station Huancayo in Peru, and it shows the normal behavior, most intense around noontime. And below, you see the temperature at the pole. It is dropping down and down all the time. This is for the year 2000. But when you go to the year 2003 below, there you see, I hope you can see it, the temperature is first dropping drastically, and then suddenly it rises rapidly by 50, 60 degrees. And then it drops again and goes up again. This is this effect of stratospheric sudden warming. And the interesting thing is that now suddenly the equatorial electrojet is heavily modulated by the lunar tide. The dashed red lines show the phase fronts of the lunar tide, and the activity of the electrojet is totally modulated by this wave. So next, please. We were interested to see whether this is systematically the way, and therefore we took all the equatorial electrojet measurements from the CHAMP, and that is the top line showing the electrojet intensity for every orbit, and then run spectrum analysis over this 10 years of data. Below you can see that in certain times we get these orange, that means high spectral density periods. This is just half the moon months, and that means this shows the lunar tidal modulation of the electrojet. And below you also can see again the stratospheric temperature at the pole, and whenever this is jumping up, the temperature at the pole, you see the strong modulation of the electrojet by the lunar tide. And in other times, the lunar tide is very weak. I mean, you can really go from winter to winter and see that it is more strong. And this was very promising for us, and this was convincing that obviously this is a systematic relation between these two phenomena. Next, please. As I said before, the sudden stratospheric warming was first observed in the 1950s. Therefore, no information was available about the occurrence of these events. And these events are very major reconfigurations of the whole atmosphere. Therefore, climate people really would know when such events occurred. Here we were taking advantage of the recordings of the Huancayo Observatory in South America, which is right under the magnetic equator. And we could interpret the data back to the years 1926. Here you can see again that the lunar tidal wave within the electrojet, or the degree of modulation of the electrojet, is varying, and always in winter time it goes up, and sometimes it goes beyond a certain threshold. Then we say that in those years there was a strong sudden stratospheric warming event. This threshold is just derived from comparison during modern times, when both electrojet measurements and direct observations of the stratospheric warmings were available. So this means the magnetic field can be very useful to identify this climatological event. Yeah, next, please. Well, it would, of course, be desirable to go even further back in the past. And one suggestion for that is one could take the diurnal variation of the magnetic field, the so-called SQ variation. Because when you run a long analysis over the SQ variation, you also find the tidal modulations there. That means one probably could go and look for historical magnetic field recordings back to the days of Gauss and try to identify also years with strong lunar tidal modulation as indicator for the occurrence of a SSW event. At least this would help the climate models to get more precise reconstructions of the back to the pre-industrial area for proper understanding of the climate evolution. And I say that historical magnetic field recordings are probably the only candidate which can be used for recovering these SSC events. Yeah, next, please. With that, I come to the conclusion. Here are my summary. The geomagnetic field, as I said, is an ever-changing magnetic phenomena. Therefore, we need continuous observations if we want to precise information about it. The magnetic field strength is getting continuously weaker, and in particular in the South American, South Atlantic region, this can become a problem in the past for our technological systems. And satellite measurements have improved a lot, but the modeling of the internal part is disturbed from signals from other sources. But on the other hand, this so-called noise component is interesting because it gives us information about processes in ocean, in the ionosphere, in the atmosphere, and so forth. And as I said, the historical recordings can probably help the climate reconstruction. Yeah, in the next, you see references and one more. So whenever you want to get full references of the papers I have cited here, or from which the papers I took the figures, you can see it from. Yeah, thank you very much.
Thank you very much, Hermann. That's excellent. Ich habe gesagt, dass es ein großartiges Gelegenheit und wir bedanken uns sehr für das. Hat jemand eine Frage?
Sie kann auch auf Deutsch kommen.
Yeah. Does anybody have a question? There's a question. No. Does anybody have a question, please? Guess everybody's shy, so maybe I'll ask a question then. Oh, here comes one.
Hello.
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 I had a question. You mentioned that briefly in passing when you talked about the crustal magnetic field, that you were quite sure that we could see subduction zones in the magnetic field. And I was wondering, because you know, the boundary between oceans and continent is always difficult to interpret. So is this something which is robust interpretation?
Well, I have just shown you the observations. Nobody has ever looked deeper into that. And I would say this observation is open for further discussion. And what you probably can see is temperature differences. The temperatures make a difference whether you have bigger magnetized block or less thick. But it should be really investigated. This is just observation here.
Okay, thanks.
Gunnar Tietze hat eine Frage.
Kann mich hören? Ja. Hallo?
Ja,
Ja. Sie haben sehr schönen Vortrag dargestellt, dass es einen meteorologischen Effekt dieser geomagnetischen Phänomene gibt. Und also diese Geschichte der kalt gefangenen Zonen in der Arktik etc. Das ist ja in den letzten Jahren viel durch die Presse gegangen und immer in Zusammenhang mit CO2-Gehalt, der vor allem an der unteren Atmosphäre sich sammelt, in Verbindung gebracht. Gibt es da irgendeinen Zusammenhang oder kann das gut auch sein, dass unsere Klimaveränderung sehr viel stärker durch die säkulare Variation und jetzt in der letzten Zeit Abnahme des Erdmagnetfeldes zu tun hat, die Sie eingangs darstellten?
Ja, also zunächst einmal, ich habe von den Temperaturen gesprochen in der Stratosphäre. Und die Stratosphäre wird nicht wärmer, sondern die Stratosphäre wird kälter. Alles, was über 30 oder so Kilometer ist, kühlt sich rapide ab. Deshalb können auch die Satelliten viel länger fliegen, neuerdings, weil die Luft da oben immer kälter und dünner wird. Insofern hat dies nicht direkt was damit zu tun, aber es gibt natürlich Rückkopplung. Es gibt eine Vermischung. Wenn diese Sudden Stratospheric Warming kommt, dann gibt es eine enorme Vermischung der verschiedenen Schichten durcheinander. Und darum ist es so wichtig für die Klimamodellierer, das zu sehen. Aber Sie haben auch recht, wenn diese Ereignisse eintreten, wenn die kalte Zone in Richtung Amerika oder Asien geschoben wird, dann haben die da auch wirklich kalte Tage. Das ist schon richtig. Also
Zusatzfrage, hat das IPCC Verständnis für das, was Sie vorgetragen haben?
Nein, die haben professionelle Sachen. Aber wir haben das veröffentlicht alles und es steht gerne zur Verfügung. Ich habe das auch schon manchmal angesprochen in Hamburg beim Max-Planck-Institut. Aber Sie meinen, Sie hätten Ihre eigenen Tools und das, ja, das wäre nicht ausgegoren.
Okay, danke, viel Mut.
Danke. Weitere Frage. Links in the chat. Sehe kein Hand. Vielleicht, ich habe auch eine Frage für die Folio 22, wann wir können gehen da. Das war dieses Disturbances von den Satelliten und es gibt einen Unterschied in Brasilien und Afrika in der Jahreszeit.
Ich kann das nicht machen, das muss der Technical Support machen.
Oder vielleicht, Sie können nur etwas sagen über, warum es gibt dieses Time Modulation, warum das ist unterschiedlich in verschiedenen Gebieten in der Welt.
Ja, also dieses Phänomen des ionosphärischen Irregularitäten ist ein Phänomen, was auftritt nach Sonnenuntergang. Mhm. Und dieses Phänomen hat etwas damit zu tun, ob der Sonnenuntergang an beiden Enden des Magnetfeldes gleichzeitig stattfindet oder ob ein Ende vom Magnetfeld im Hellen ist oder ein ins Dunkel ist. Und das ist die Hauptursache für die Verteilung, dass eben es am besten funktioniert, wenn beide Enden von einem Magnetfeld im nördlichen und südlichen Hemisphäre gleichzeitig in die Dämmerung gehen. Wenn ein Ende, wie gesagt, wenn ein Ende noch in Licht ist und das andere in Helligkeit, dann entstehen diese nicht so schnell. Das, ja, insofern, also dieses Bild, was ich gezeigt habe, sieht vielleicht etwas gefährlich aus, aber es sagt aus, dass Champ an einem Tag irgendwo eine Störung gesehen hat. Und das heißt, dass nicht die ganze Zeit Störung ist, sondern eben nur die Wahrscheinlichkeit, dass man eine Störung findet an einem Tag, ist meinetwegen 80% oder 0% oder so.
Okay, ja, danke. Ich schaue hier nochmal in den Chat. Ich sehe keine andere Frage.
Ich will auch gerne den Vortrag zur Verfügung stellen, wenn jemand sich den kopieren möchte oder so.
Ah ja, okay, danke.
Kann noch einmal schauen, aber darum habe ich auch die vielen References richtig explizit hingeschrieben, dass man sich da auch selber noch schlau machen kann.
Okay, dann vielleicht wir können bedanken Hermann Lühr nochmals für dieses wirklich klares Vortrag, das er hat gegeben und sehr breit und immer erstaunlich, wie viel wir können lernen von diesen Satellitendaten so bis von 1000 Kilometer hoch bis zum Kern. Danke.
Ja, danke schön auch von meiner Seite.
Ja, okay. Danke an alle.